Today we're going to be talking about how to use second-order linear homogeneous recursion relation. In this, there are two separate sections. One was distinct roots and one was repeated/same roots. In both of these, a0 is equal to 1, a1 is equal to 0, but in distinct roots, an is equal to 5n minus 1 minus 6 times an minus 2. So how do we use second-order linear homogeneous recursion relation? Well, we used it in equation 3. So we replaced an with x squared, an minus 1 was x, and an minus 2 was 1, which doesn't really change much, huh? So now, so why does this happen? Well, we can, with n, the difference between n and n minus 1 is 1, so is the difference between 2 and 1. So it just keeps on going till it reaches the n, which here is an minus 2, which is n was out of x. By the way, if you have an equation like this with a sequence, you can't use second-order linear homogeneous recursion relation if there's a constant with it. If it has like a 2 or anything else, then it won't work and you try to use a different method. So now the roots for x in this equation are 2 and 3 by solving the equation, of course. So now the second part of second-order linear homogeneous recurrence relation is that an is equal to c times 2 to the n power, which is 2 over here, times 3 to the n power, which is 3 over here. So now we have to solve the value of c and d. But how do we do that? Well, since we know the value of a0 and a1, we can just put the values of those in. So 1 is equal to, I'll just put it in. C plus 1 is equal to c plus d, and 0 is equal to 2c plus 3d. This makes it so that c is equal to 3 and d is equal to minus 2. Putting this into equation 4, we're going to get that an is equal to 3 times 2n minus 2 times 3n. And there you go. That's the equation for distinct roots. Next is repeated/same roots in second-order linear homogeneous recurrence relation. This time, we do the same thing as we did in this example here. However, we only get one root instead of these two roots over here. Well, technically it's two roots, but it's the same root, just 2. So, do we use the same thing as before, or do we have a whole new formula for it? Well, the answer should be obvious. We have a different formula for it. That's why we have a different section for it. In this, an is equal to c times 2 to the n power, the same thing so far, plus d times n minus d times n times 2 to the n power. The only difference between these, despite having different root, is that it's multiplied by n in the middle. So now we can do the same thing as before by substituting the values of 0 and 1 into these equations over here. We get that 1 is equal to c, c, and 0 is equal to 2c plus 2d, making it so that c is equal to, well, still 1, and d is equal to minus 1. This also makes n equal to 2 to n power minus d times 2 to n, not d, sorry, minus 2 to the n power times n. And we're done with these two examples. Now we're going to move on to our next one, involving the Fibonacci sequence. Next example in second-order linear homogeneous recursion relations was the Fibonacci sequence, where a0 is equal to 0, a1 is equal to 1, and an is equal to an minus 1 plus an minus 2, when n is greater than or equal to 2. So let's just do what we just did with the last two examples. Now an is equal to x squared, an minus 1 is equal to x, and an minus 2 is equal to 1. By solving this equation, we get that x is equal to 1 plus minus square root of 5 divided by 2. The plus minus here just means that x can either be equal to 1 plus square root of 5 divided by 2 or 1 minus square root of 5 divided by 2. So those are our two roots. Then we get this equation over here. The same one we use the same formula as we did with our distinct root example. An is equal to 1 plus square root of 5 to the n power times c plus 1 minus square root of 5 divided by 2 to the n power times d. Putting the first two equations into this over here, then we get that 0 is equal to c plus d, and 1 is equal to 1 plus square root of 5 divided by 2 times c plus 1 minus square root of 5 divided by 2 times d. By solving these two equations, we get that c is equal to 1 divided by square root of 5, and d is equal to 1 minus 1 divided by square root of 5. Putting those two values in the equation over here, and we get that an is equal to 1 divided by square root of 5 times 1 plus square root of 5 divided by 2 to the n power minus 1 minus square root of 5 divided by 2 to the n power. And there we go. That's our answer for second-order linear homogeneous recursion relations with the Fibonacci sequence.